All right, so we're going to talk about independence in today's lesson. I want you to pay special attention to understanding the difference between when two events are independent and when they're mutually exclusive, because people can tend to mix those up even though they're practically the opposite. They cannot exist at the same time. All right, so here's our definition of independent. So when knowledge of that one event has occurred does not change the likelihood that another event will happen, we say that the two events are independent of each other. And so kind of the formula that simplifies down to is if I have two events A and B, and I can show that the probability of event B occurring given that event A has occurred is the same as just the probability of event B occurring by itself, then we say that the two events are independent because knowing that A occurred did not influence the outcome of probability of event B occurring. All right. And so for independent events, that simplifies the multiplication rule for us because, and I'll write this out, remember that the general multiplication rule was the probability of event A and B occurring together is the probability of event A occurring times the probability of event B occurring given that A has occurred. But if we know they're independent, then notice that we said the probability of event B given A is just the same as the probability of B. And thus this would then just simplify down to that. Okay, I'll give you a second on this slide to make sure you get these definitions down. Give me a green check when you're good. If you're asked to show that two events are independent, this is how you're going to show it. Okay? Sort of a trap that students tend to fall into is they're asked to show that or explain why two events are independent, and they give just a verbal explanation where they just say, knowing that this event happens doesn't change the likelihood that the other one will happen. Great. Now, prove that to me with numbers. So anytime you're asked to show, you need to show that, right, the conditional probability equals the original probability and that the condition didn't affect the outcome. All right, so you don't have to write this example down. I don't even know if you guys have heard of this, but do you guys know about the Space Shuttle Challenger? Have you heard? Yeah, okay. Do you learn about that in history or do you just know it from like random trivia? Or is that like something that's actually talked about in classes now? So it was an extremely traumatic event from when I was in like kindergarten, and they sent up, right. So if you've just, this may be redundant. You guys all said you've heard of it. So, but they like the thing was they televised it, and it was a national watch. Like at schools, everybody across the country was watching it because they were sending a teacher up, and I was in kindergarten, and yeah, so we were all watching it, and then it exploded on live television, and people were horrified, and parents all went and picked their kids up and were afraid that everybody was traumatized, which, you know, the nation was, but now tons of worse things have happened. So we're much more traumatized at this point by other things. But the whole thing that was happened was that there were these O-rings, these gaskets in the shuttle's booster rockets, right, that were meant to seal the fuel from the fire, essentially. And under cold conditions, it was estimated that an individual O-ring joint would function properly was 0.977. And if we assume that they succeed or fail independently, what's the probability that all six would function properly? So this is the key. In a problem like this, if they say independently, you'll go, I can just multiply their individual probabilities together, right? So if I want to know the probability that all would fail together, or sorry, in this case they're saying that all would function properly, rather, I would want to multiply the probability that each one functions properly by itself. So in this case, that's 0.977 for each O-ring. So I end up with just 0.977 to the sixth, or about an 87% probability. And so there's an 87% chance that the shuttle would launch safely under similar conditions, and a 13% chance that it wouldn't. Which 87% isn't bad, but when it's literally a life or death situation, that's probably not a probability you want to rely on. You would want to launch. And that was the whole thing. They launched in conditions that were too cold, and the O-rings seized up and failed, leaking fuel right into the boosters and exploding the rocket and traumatizing a young Robert Toller in kindergarten. All right. So I'll do kind of a concrete example. Is the Diamondbacks, in the Diamondbacks example from the 5.3.1 notes, are the events T and W independent? So I'll just real quick redraw the table we had. So we had tacos and no tacos, and we had win and loss, right? And so I don't remember which axis I put which on, but I'll do it like this. So we'll have win and loss, and then we'll have tacos and no tacos. All right, and then I'll fill it in with Diamondbacks won 41 of their 81 home games. So that means they lost 40. They got free tacos in 30 of their 81 home games. So that's 30, and that means 51. No tacos. And then in 26, they won and gave away free tacos. And so that means in 15 won and no tacos, 4 lost, still got tacos, and 36 no tacos and lost. All right. Are the events T and W independent? So if I want to look at independence, I want to go, is the probability of getting tacos, given that we won, the same as the probability of getting tacos? If that's true, that would imply that the events are independent. Because knowing that we won doesn't influence the probability of getting tacos in that case, right? All right. So let's just do the right-hand side first. What's the probability of getting tacos? Well, we got tacos in 30 out of 81 home games. So it's just 30 out of 81. All right, what's the probability of getting tacos given that we won? So this is now narrowing our population of interest just down. Oh, no, I'm sorry, I circled the wrong one. Just down to the given that we won. So we're just looking at we won. So our total is going to be out of 41. How many of those did we get tacos for? 26. So 26 out of 41. All right, well, they're kind of hard to compare when it's in fractional form. So 26 out of 41 is about 0.634. And 30 out of 81 is 0.37. Oh, those are decidedly not equal. Therefore, T and W are not independent. Meaning, knowing our winning status influences the probability of whether or not we get tacos, which makes sense because getting tacos is dependent on a number of runs, and you're generally going to be more likely to win if you get more runs. So you would expect the likelihood of getting tacos to be higher if you win in most cases, right? But since those probabilities are not the same, events tacos and winning are not independent. Meaning knowing that one occurred does influence whether or not the probability of the other one will occur. Okay? And so this is the work I would need to see to prove whether or not these are independent. If they came out equal, they would be independent. All right. So two events cannot be both mutually exclusive and independent. In fact, if they are mutually exclusive, they are not independent, and vice versa, because mutually exclusive means they can't possibly occur at the same time. Okay, take the scenario where I flip a coin and my outcomes are heads or tails. Would you agree that those events are mutually exclusive, meaning they can't occur at the same time? You get one or the other. So I agree. These are mutually exclusive. So the thing that I'm saying is they can't possibly be independent, and here's why. Let's say I flip the coin. To be independent, the probability of getting heads would have to be the same as the probability of getting heads given that you got tails. What's the probability of getting heads, just in general? Well, if it's a fair coin, that's 0.5, 1 out of 2, right? What's the probability of getting heads given that you got tails? Can you put that in the chat for me? So you already flipped the coin. I'm giving you that you got tails. What's the probability that you get heads then? It's 0. We're only flipping the coin once. So if I tell you that you got tails, the probability that you get heads, the outcome is 0 because they're mutually exclusive. They can't occur at the same time, right? So these are obviously they're not equal, right? So not independent. Two mutually exclusive events can never be independent. And two independent events won't be mutually exclusive. All right. I'm going to save this one. We'll do it as maybe a warm-up just real quick before we do our APFRQ. Just because we did two problems now, with the warm-up was this type of problem, and I showed you my example of the antibody test, which was the same type of problem. And I want to make sure and just show you the last example first, but we'll do this as a warm-up for Wednesday. Last one, on a recent day, the Arizona Star forecast a 50% chance of rain in Oro Valley and a 50% chance of rain in Marana. what's the probability it will rain in both locations? So these locations, I will tell you, are both in southern AZ. This book's funny because the authors are from like the Tucson area, but this is like the most widely circulated AP statistics test, so it's used around the country and around the world. But there's all these examples that are like weird southern AZ specific examples that people are probably like, what Marana? What are these made up towns? But that's important to know for this example. I'm not just telling you that as an interesting anecdote. So we can only multiply probabilities, right? You might want to go, okay, probability that it will rain in Marana and Oro Valley. I'll just multiply them, 0.5 times 0.5. Oops. The problem with that is to be able to do that, we have to be able to know that these are independent. And so you either have to have that stated in your prompt, and if it's stated in your prompt, it's okay to make that assumption, and then it's okay to multiply individual probabilities, right? Or there has to be some reasonable assumption of independence, meaning it's probably okay to assume that the weather patterns in Phoenix are roughly independent of the weather patterns in New York City. There's enough space in between us. Now, that's technically not true, right? We have a world weather system where all things are dependent on each other, but that's what we call a chaotic system, where there's too many variables to really mathematically account for it. So they're probably roughly independent. But cities like Tempe and Mesa, would it safe to say that those weather patterns are independent of each other? Is it going to be sunny and 120 in one and rainy and 60 in the other on the same day? Probably not. They're close enough that they're going to be dependent of each other. It's not safe to assume independence. And since these are both from southern Arizona, I would say that it's not safe to assume independence, and we can't calculate the probability. So this is a trick question. You won't be asked a specific trick question like this in the problems that are on the test, but you could be asked, can you calculate this probability? Like, this is, the wording here is a little bit too tricky. They're acting like there is a probability that you'd be able to calculate. But if you're asked, can you calculate the probability, that's when you want to make sure you're checking the conditions under which it's safe to calculate the probability. AKA, are the events independent, before you start just multiplying things out. Does that make sense? All right, we're going to stop there.